Welcome everyone to the second seminar in this series organized by the G5 Commission of the IAU. Today we have Sergey Yurchenko, who's going to talk about the ExoMol project, which I think is going to be of interest for the vast majority of us. We also count today with Chris Snedden, who is the incoming president of the Commission G5. We're very happy to see him participating as well with us on this. He's going to be moderating the questions at the end. And we also have Daniela Korkakova, who you will know from the previous seminar, and is one of the organizers of this series. She's going to introduce Sergey. So please keep your microphones muted and also your cameras, unless you know, are going to pose a question or to pose a question to the speaker, and you're invited by Chris. Please, Daniela, go ahead.
Okay, thank you. Welcome. It's my great pleasure to invite here Professor Sergey Yurchenko. He will talk today about his work on molecular spectra. Sergey started his career at the University in Tomsk, where he obtained a master and a PhD degree. After that, he also continues work at this university. After some years, he moved to Ottawa, to NRC, where he worked in the field of theoretical chemistry. He continues working in this field at Max Planck Institute, and after that at Technical University in Dresden. Since 2011, he worked at University College London, where he is now professor of physics. As I know, his start at England was nothing so easy, and I have to thank him that he didn't give it up, because the work which he did there is unbelievably great. He's the person who is behind ExoMol database. This database offers a line list of more than 80 molecules, and not only a line list, also other necessary data for calculating of synthetic spectra like opacities and cross sections. And moreover, they give in the most important programs to GitHub database, so everybody can download it and use it or play with this. So for all these works, I really thank to Sergey. And so please, can you say us more details about it?
Thank you. Thank you, Dana. That was my pleasure. So thank you very much for the very nice introduction. Thank you for coming here. It's my great pleasure to present our work. I'll try not to be too theoretical chemistry in my talk. Now I'm also an astronomer, and I started with the quantum chemistry. So let me then share. And check that's actually working. Yes. Perfect. Okay, good. So I think I'm ready to start. So, hi everyone, I'm Sergey Yurchenko. I'm from University College London, and I work on the ExoMol project. There are other obviously projects where I'm involved with as a quantum chemist, as an astronomer. That's my main contribution to the astrophysics. So precision spectroscopic data for studies of exoplanets and other hot atmospheres. So that is what we produce. We produce and collect accurate spectral data for all molecules likely to be important for exoplanetary atmospheres. So basically our main product is line list. And that's, if you think of this line, we list basically line positions and line profiles and all other properties which are important to model synthetic spectra of these molecules. So the group, so I present the group ExoMol, and we started ExoMol with Professor Jonathan Tennyson in 2011. It's many people so that contributed to this. This is a snapshot of 2019, obviously, for the obvious reason. So now there are more people in the group, and some left, but that's a good picture to show. So let's talk about exoplanets first. First detection of exoplanet orbiting a star is back to 1995 by these wonderful people, Michel Mayer and Didier Cuelis in 1995, and now they are Nobel Prize winners for that. Since then, the exoplanetary field basically exploded. Now there are several thousands of exoplanets have been detected and hundreds characterized. So now we know they exist, which wasn't the case before this time when the first exoplanet was discovered. And now we want to know why they're so exotic, what they are made of, how they form, what's weather like there, and other stuff. The main source of answers is and used to be is a spectroscopic technique called transit. And transit is basically detecting variation of brightness of a star eclipsed by a planet. So let me show you this figure. This picture when you have a star, the planet going in front of the star, and we measure the brightness, and there's the flux. The stellar flux will obviously drop when the planet will go in front of the star. That's what we can measure. And transit curves, and we call them transit curves, and they can be different. So, for example, the typical transit curves for some planets like Kepler 4b, Kepler 5b, 6b, 7b, 8b, and you see that they're all, in this case, very short orbits from 3 days to 4.9 days, and they have different shapes, which is obviously interesting and important. Some of them can be very interesting. So look at this Kepler 1625b curve, especially at this particular wiggle, and that's one. So it's argued that maybe it's because of the signature of ExoMol accompanying the planet in the transit. Still not fully proved. Or of a super Earth 55 country E. So just look at this very strange the transit curve. So that's for example, this part is that's when the planet is in front of this star, and everything after this is when it's not, and that's the one at the right hand side is when it's behind. So and look at this strange variation of the brightness of the star when the planet passes in front of the star and afterwards. And it's the explanation from the author of the study, for example, is because it's losing that atmosphere. So this isn't cool. That's just based on the transit curve, you can obtain already information on the property of the atmosphere of the planet. Okay, I'm a spectroscopist. It's called Hubble spectroscopy, and it's basically the same thing. What we want to do is to look at the variation of the brightness of the star at different wavelengths. So we look at different wavelengths, and they obviously. But what can happen if the planet has an atmosphere and the different wavelengths, if this light will be observed, then this planet would appear either bigger or smaller. So let's say if there is water and observed water observed, and on this particular wavelength, the planet would appear more opaque and larger. And that gives us an exoplanetary spectrum. It typically looks like that. And just look at the y-axis. So it's the ratio of the planet to the radius planet or the radius of the star, which is not what the spectroscopists are used to. And the resolution of exoplanetary spectra is very low. Even in the best cases, there are no distinct spectroscopic lines or even bands. And the error bars also big, and the spectra can be flat and featureless. As well is very complex. Like this study of different they put together different spectra of different exoplanets, and you can see that they're different. They scale with temperature, and they also more or less clustered at the visible and also the near infrared, and it's because represented by the biases of the observations. So this is the Hubble range, infrared range, and the quality of data is obviously not great, but still one can learn a lot. So Exoplanet HD209458b, for example, this is the spectra which is obtained as a transit spectrum, and the represented transit depths as a function of wavelength, exactly in the Hubble region. And if you think of this, this is Jonathan Tennyson showing the feature at the middle, which is clear water band. So that's even these low resolution, you can already detect water. And maybe this is ammonia and HCl that models, atmospheric models do agree with this conclusion, but still you need more accurate data and more data in order to confirm this. And usually water and methane is usually first to find, and especially water. This is another example of the hot Jupiter HD209458b. So here's the spectrum. So the points represent the actual observation data, and everything else are different models. Models real water, water in methane. So this is clear, again, clear water in the orange curve is represent theory. And this may be methane, but I don't know, maybe not. And one of the most recent exoplanet discoveries that we participated in was the water vapor in atmosphere of the habitable zone 8 Earth mass planet K2-18b. And here's again the spectrum. The points represent the observations. Everything else comes from our model. And this is one of the modelers, Inga Waldman, showing this is clear signature of water. So what we do at ExoMol, we provide theoretical molecular data for atmospheric retrievals. So we tell the water, by the methane, and how much and how these species observe or emit. And we call them molecular line list. So basically represented absorption emission properties of molecules populating atmospheres of exoplanet and cool stars. We apply quantum mechanics. So that's where my quantum chemistry background comes from. We solve Schrodinger equations for the motion of electrons and nuclei. I realized maybe that's not the quantum chemistry audience, that I would like to show that roughly draft the procedure. So we solve it from first principle. That means we first reconstruct how the potential energy depends on the distance, on the internuclear distance. And that is represented by a potential energy curve. We take this potential energy curve, combine it with that dipole moments, plug it into the Schrodinger equation solver. In our case, it's a home base, the program written by us, do a program, and obtain the solution as well as all Einstein coefficients, intensities, which produces our line of sight data. I should mention that the pure theory is never good enough. So all of initial potential curves and the theoretical line list are not useful without further improvement by comparing to the experiment and improvement by fitting to the experiment. So it's always a part of the procedure. This is a very simple example. In reality, most of the systems are not so simple, it's not single state. For example, if you take yttrium oxide, one of the systems which has been observed in the stellar forming regions, and that's if you take a look at the initial curves, it's a complex system of different electronic states, and the dipole moment curves are much more complicated. But also you have to deal with the spin orbit couplings and other electronic angular momentum couplings. And they're complicated but solvable. It's just not so easy as for simple diatomic molecules. And they again have to be everything have to be refined. And the shapes of the spin-orbit couplings and the dipole moments is not so pleasant, and we have to deal with that. And similar strategy is used for polyatomic molecules. I don't go into there. The main difference is that the size of the problem is much bigger. So we are dealing with billions of lines when we computed the spectra of these molecules, especially when dealing with hot temperatures. What is important for the hot atmospheric studies is to be complete. And that's the main kind of strength our methodology comes from. This is where theory can be very useful. Because experiment in most cases, I would say almost all cases, is very incomplete. Here's my favorite illustration, a cool star spectrum at high resolution. It's the ground for T4.5. And what I show now is the real observations. And it's again, it's the favorite region near infrared. And what you can see in the middle, close to the middle, is no methane band. And if you take only empirical data, kind of experiment which you use in order to build your empirical model, and try to model this, you clearly see that you can't. There is a problem. Something is missing. This is still methane, but something is missing. So we put in a huge effort and computed the 10 billion line list for methane, and this is our theory, which fits perfectly this pattern. And this we kind of moved for the completely unsolved problem to the solved problem. And apart from the observations, which extremely very well. Now, if you're wondering why this disagreement on the right hand side, it's actually it's not methane. It's a different problem. It's CIA. We're still working on that problem. So it's a different physics. Okay, here's another example: spectra of phosphine. And you have probably seen the recent discovery of phosphine in the atmosphere of Venus by our former ExoMol PhD student, Clara Souza Silva. And she computed the phosphine line list, and experimental phosphine was very incomplete. And here Clara is showing the difference. So in my talk, Haitran basically means experiment. So Haitran, and whenever you see this on those slides, Haitran represent the general collection of all experimental data for a given molecule. And you can see the number of points data known for Haitran is very, very low comparing to the full phosphine, Clara's phosphine line list. So we aim to provide all the data necessary to model atmospheric absorption emission, even at elevated temperatures, and have built an efficient machinery for accurate productions of molecular spectrum for atmospheric applications, stars and exoplanets. And here's my kind of slide representing the sales slide, if you like, salesman. So example, why you would like to use an example like this. So it's a current leading provider of molecular data, important sources of exoplanetary opacities, covering large wavelength range. It has trillions of transitions, and applicable to large temperature variations. And actually, this year is our 10 years anniversary. We started in 2011, and this is where we actually started with these molecules, which were available before us, not fully complete, but reasonably good shape. And this is where we are now in 2021. So it's more than 80 molecules. And if you count isotope logs, it's more than 240 isotope logs. And like I said, it's close to 1 trillion lines. Everyone is computed with our machinery. So red shows you kind of difficult problems or something in progress, currently in progress. And these ones represent part of our current project. Is a spectra for lava planet species, for lava planet. So this is where we are today. So I showed you methane. TiO is another important example. TiO is one of the most important molecules for exoplanetary studies, effectively, and used, for example, to discover stratosphere of exoplanet WASP 121b in 2017. And here's an example of WASP-1221b spectrum. So this part again, this is water. So, but this is argued to be TIO and OVO emission. And that the lower image produced this this line list for VO and TO, showing the contribution to the atmospheric absorption emission. And the thing that's what the explanation of this is TIO and VO play a similar role to that of ozone in the Earth atmosphere. So they absorb the radiation and heats this upper layers of that atmosphere. That's how that from the atmospheric temperature inversion you can then build tell something more interesting about the physics of the atmosphere of the particular exoplanet. However, so that's all I talked about the completeness, how we contribute to the completeness of this problem, and general and low resolution as well. However, there is one very important message that we learned recently. That actually it's not only completeness matters, but also high resolution, and that so not all ExoMol at least really directly applicable for high resolution studies, which are now becoming more and more important. So together with John Tennyson, we're now moving into this direction with the goal of solving the problem of high resolution. So why is it a problem? So because of the high resolution Doppler technique, which is now it's a new emerging technique which is playing a huge role in exoplanetary studies. So what is it? And that's if you think of one of the examples is the emission of CO detected in the Tau Boötes B planet. So in this case, it's not in transit, so you can't really see it in the transit. You can't use it for this. However, while being orbiting the star, obviously you can detect some wobbling of the star, but it's not about this. But it's more interesting that if you think about the lines of the emission lines from the atmosphere of the exoplanet, because of the Doppler shift, and you know the velocity of this planet, you can actually predict where these lines will be if they would be emitting from the atmosphere. So this is what you see. You don't see the planet, but you can imagine that you can see these lines. Obviously, you need to have many lines in order to say something. So you take your CO spectrum and correlate it to what you see, and that by also correlating to the velocity of the planet that you know. And by doing this, you increase the sensitivity, the signal to noise ratio, and you get your detection. And that's how that, for example, water and high resolution spectrum using high resolution spectroscopy was detected on 51 Pegasus B. And this is how it works. So you take highest VLT data, which would look like that from the ground, and you normalize it, and you remove telluric lines, and you do another pass of the telluric lines removal, and you see kind of noise, kind of white or gray noise. But then you correlate it to water, and you start seeing the very nice features of water and the specific wavelengths, but you know where the water lines are. And then you get a very nice correlation signal, which in this case close to 38 kilometers per second, exactly where it should be. That's your detection of water. So this is super cool, and that we noticed that people started using our data for high resolution modeling. However, they had some problems with this, and sometimes depending on the quality of the data. Sometimes it worked perfectly, so like water detection. With other molecules, you would sometimes see this kind of two types of reaction. Wait a minute, there is no molecules there. Very strange. You see the noise, you see no correlations. Oh my God, ExoMol is broken. So we realized that something was not there, and that we needed to deal with this. And it's this high resolution. And it was our totally fault. We cannot really properly explain the limitations of our data. And the truth is that not all lines in ExoMol are high resolution proof, and those which are shown in blue. And most of them are diatomics, because diatomics are just easier to do. And let's say our new water line list is good even for high resolution, but not, we can't say that's for everything. And TIO is also perfect for high resolution studies. So let me explain why. So our main goal was to provide line list, both accurate and complete, and accurate line positions, accurate line intensities, but most importantly, applicable for large wavelength ranges and hot temperatures. These priorities are, however, not always compatible. It's very difficult to deliver both, be complete and accurate at the same time for everything. It's too difficult, just too difficult, or even sometimes impossible to do both. Luckily, most applications don't require to be both accurate and complete. For example, most of the opacity applications, atmospheric retrievals, require to be complete and not so much accurate. Like in the case of water detection, you don't really have to have high resolution in order to tell this is water. It appears exactly where it should be and also fulfills all the modern requirements. And for high resolution, Doppler high resolution applications, the completeness is not so much important. So we decided to concentrate on this distinguishing these two main features of the problems. So for example, the data for the high resolution must be accurate, but not so much complete. So still, we will try both, and that's our goal. This, for example, an example of acetylene line list at room temperature, and we use experiment to improve our theory. Untitled Chapter is showing her line list for acetylene. And then if you go to high temperatures and compare to the existing experimental data at 1000 Kelvin, you will see that the experiment is incomplete. We provide full coverage, however, only guarantee that our accuracy at the ranges where we could directly compare to the experiment. And theory maybe is less accurate in these ranges in between the experiment data, but complete. This summarizes the main computational strategy of ExoMol. This is recently. So this is the example of ethylene line list, complete and sufficiently accurate, computed by Pariman. And it contains 50 billion lines, good for all the retrievals, but maybe not so much for high resolution, or not everything high resolution. So for high resolution, we usually would recommend to use High-Tran, so that the data, the High-Tran database where the experiment data is collected. However, High-Tran is obviously not very sufficient. And this is the example, the ammonia. So here, Phil Coles is showing his ammonia spectral line list. And here it's on the upper part is the experimental data, and you can see compared to the full description of the absorption of ammonia, it's very sparse. And you can see that there are many places where it doesn't exist at all. And theory may be less accurate by complete. And that's what could happen if you try to look at the different planets where you would expect ammonia to absorb. This one of the bands from 3,300 centimeters minus 1 at room temperature. So that with the experimental data, you would be fine at low temperature. However, now if you want to know what happens with the spectrum, if you increase the temperature to 1500, then you will see lots of new lines, which will completely kind of fool the space. And that's something that you can't rely on experimental data on. Okay, as a response to the new requirement, we studied project ExoMol in HD, high definition. That's our new thing. That's what we do, and I'd like to show what our strategy for that and how you can use it. So our goal is first of all, obviously, to provide as many theoretical, as much accurate as possible for as many lines as possible, but also give uncertainties for all lines, such that everyone who's using this the outline list would know what to use. So for simple atomic molecules, it's relatively easy actually to provide the HD quality, even with the standard ExoMol approach. And that's this example of magnesium oxide, data comparing to the experiment. So red is our data, and blue, also black, is experiment. And that's the line list recently published. Well, high resolution is less straightforward for complex diatomics, and actually vanadium oxide or tin oxide is one of those difficult transition metals diatomics, which are not easy to do, or polyatomic molecules. So for those, this is what we apply ExoMol strategy, and I want to walk you through the main idea of our improvement. So here I show the water spectrum at 1350 Kelvin. And the upper part is experiment, and the lower part is our initial line list, initial theory. So it's sort of okay, especially for water. We did a lot of work in order to guarantee the quality of this data. Still, it's not perfect. It might be decisive when you try to detect water in this particular wavelength. So we take our best theoretical data, and you can see they don't always match the experiment. Like I said, that might be crucial. And this particular example that I show is one of the best examples. In most cases, it might be worse than that. So what we do then, we replace theoretical lines with experimental lines directly. And that obviously improves those which we can improve, and still preserve the intensities and all other lines. So it's a very simple strategy that it works the magic. So then our best ExoMolHD lines, this one for water shown at 1300 Kelvin, perfectly match the experiment, and we always compare to the experiment. And we call this procedure marbleization. And it's just because we use this open source program, which stands for Measured Active Rotation Vibration Energy Levels, where we take experimental spectra and work them to produce energy levels of the upper state and lower state, and then we're able to replace our data with this accurate data from experiment. So we call this procedure marbleization. And then this example of the new ExoMolHD line list for water, and the upper display shows experiment, lower display shows theory, which are perfectly in line, and the intensities are in good quality. And this example of the line list called populating. Important, not all lines can be and will be marbleized. Just because we don't have experiment data, it's very difficult to produce experiment data for everything. So that is why we decided to provide indication which lines are in HD by any lines uncertainties, which is not so straightforward, and it's really not so much easy, not very easy, because sometimes we are dealing with billions of lines, and for different vibrational and rotational states, and deciding on uncertainty is not really trivial. But we see that it's hugely important, and we would like to recommend using non-marbleized lines with high resolution applications, and watch for the uncertainties that we provide. And one of the most recent example of marbleization is the formaldehyde line list. And that's what I show in the bottom display is experimental data for everything which existed on the formaldehyde absorption. And the upper display is a combination of in the green is the full thing that should be produced as an ExoMol capacity, and also for any temperatures. And it shows a marble contribution to this. So those lines which were marbleized, which have the quality that one can use for the detection of in high resolution studies. And that basically summarizes that's what I wanted to say. So we provide lots of data. So it's trillions of lines. And now our focus, not only on completeness, but also on high resolution. So that's all I wanted to say. So thank you for your attention.
Thank you, Sergey. Folks, the floor is open for questions. Okay, now what I have to do is figure out how to do this. Let's see. I have to find the any upraised hands. I may need some help here, folks, if anybody sees any.
Yeah, Jason, I think you see Jason's.
Sorry, I'm missing. I'm missing seeing any raised hands.
Yeah, you have to look at the participants list, which is in one of the buttons.
Okay. Yes, yes. Okay, how about let's see. I'm seeing you really abbreviated looks at who are on the screen. Give me a half a sec. I'll get there. There we are. Okay. All right. Martino Sosorio, doctor, could you please unmute yourself?
Yeah. Thank you very much. Thanks a lot for the talk. It was very enlightening. That's very cool. And I have many questions, but I will just do one. What are the plans about non-neutral molecules? I guess you are working always with neutral molecules, huh? Or do you plan to do something with some ions, with some charged molecules, or?
Yes, yeah. Thank you. It's a great question. So I've got 2 points here. With exoplanetary applications, the non-neutral molecules are not so much important because they don't live too long in order to produce a kind of big contribution, except as a few cases, most important ones, like for example the He plus or HCO plus or HCO plus. So there's a few things which are expected to be important, and as a response to this possible application, we produce line list for those which we consider to be, might play a role. Like I said, He plus, HCO plus. That's which are now done and available and waiting for the discoveries. But it's like I said, there are 2 points. The main point is that if you only think about the exoplanetary applications, there is no so much big market for ions. But we are not only working for exoplanets, we also do produce data for everything else. So we do have a few ions and ready to produce more if there is need. So you can have some specific.
Yeah, I think the people of cool stars, the coolest stars, the very cool stars, they do have the need. Maybe you can have signs for ions in there. And so for sure there is contribution from the continuum in there, but I don't know, there might be bands or things like this that might also affect the opacity in an important proportion to the.
Yeah, absolutely. So my suggestion to this, just if you have some interest, look at our database, and if you don't find this molecule, let us know, and we will do our quantum mechanics to produce line list for this for the species.
Cool. And I thank you. And I have another question about:
Yes.
Do you have plans, or is there something that you have thought about regarding collisional processes, like more interactions, things going more towards hopefully one day having non-LT applied to molecules directly or things like this?
That's a very good question. When I'm working on non-LT, it's more or less kind of empirical approach. So we're not at the moment combining with the collision rates. It's more like that. So we use this by temperature description of the non-LT, kind of rotation temperature, vibration temperature.
Okay, cool.
Yeah, but it's the next step to do to include these collision rates for the proper description. We're planning to work on the collisions more in terms of the line broadening.
Yes, I see that word. That was very cool. The one that you did with water. That's good. Thank you. Thank you very much.
Okay, Eduardo, would you unmute and ask your question, please?
Sure. Hi. very nice talk. I really enjoyed it. I have one question and one comment. The question is, in your website, which is very useful, we can download a lot of your data, your well, theoretical data. I wonder if there is also a way to download the reference experimental spectra or observational spectra that you are using to do the calibrations that you mentioned, such as like the marbleization. So is that also available?
No, not really. That's maybe the problem. The main problem is that we often combine tens or hundreds of different experimental data, and that we process them in order to full, complete, self-consistent set. And then we do this, we invert it, and we get energies which we then use to improve our line list. But it's this data that the experimental data, all this goes as a part of this Marvel publication. And also should be also available from the Marvel website as well. So if you are interested in this one combined self-consistent set of the experimental data extracted from all the sources, then it's always a part of our publication, right? So you can always find it, not from ExoMol website, if you go to one of the publications that were used as parts of the process, then you always find the data, or you go directly to the Marvel website. And maybe it's not easy to find it because it's not easy to search for anything related to Marvel, but I can provide a link to this, and they do this work. They collect this the self-consistent set of experimental data that we combine there on this Marvel website.
Okay, and the comment is that at the IEC we are developing the capability of getting laboratory spectra, and
it's really cool.
We could perhaps collaborate on some molecules where we're taking several molecules right now. It's just at the room temperature in the optical laboratory, and well, we have a wavelength range from optical to the near infrared, because we're using a carry spectrograph to get the spectra, and we're getting the gas cells are being made at the chemistry department of the university. So we're playing with some of the molecules of interest for brown dwarf atmospheres, and because we also want to have this comparison, so the ExoMol data, the Hytran data, and also our own resource to compare with the observational spectra that we can get in the observatories here in the Canaries. So just to comment on that, we have not published much. In 2010, we had a PhD student that published a set of laboratory spectra, but maybe you didn't, maybe you're not aware of that paper, because really the main focus of that paper was to try to find some like a cell that would be a wavelength reference, similar to the iodine in the optical, but in the near infrared. So we made a complex mixture of gases, but and that was the goal at that time. But now we are keeping on developing that for similar purpose of what you are doing, but from the experimental side.
Yeah, that's amazing.
If there are any molecules that you will be interested, but
plenty. Yeah, there's always kind of related to the specific to your experimental setup, right? And maybe slightly also there's some constraint from your experiment, then would be good to understand this. And then I mean, we need many things, lots of things. And then once we can understand what you can provide, that would be interesting to give you kind of our wish list, or maybe from your side, maybe your wish list on the data you would like to see.
Yeah, okay, we can continue offline.
Yeah.
Thank you.
Okay, are there any more questions? Let me then chime in with questions. I'm a pretty typical stellar spectroscopist interested in cool stars. First off, thanks very much for clearing up the distinction between ExoMol and HITRAN. That isn't obvious if you're not in the molecular physics field. But that raises a question. In your talk, you said, hey, we've recently updated this molecule and that molecule for high resolution. How do I know that in my work? And if the answer is not obvious, then of course the obvious thing would be, boy, it'd be nice to get messages on the main page of your website.
Yes, yeah. So if you want to know which molecules are suitable for high resolution studies, if you just go to the specific molecule website, you will see that it says on the line list, this is marvelized, right?
Okay.
Right? That's one thing. Regarding the updates, it's always, I don't know, not so trivial to find the best way to notify people. I don't know. We tried several things, like to provide the updates on the website, say something. Usually people don't really check websites, so,
yeah.
Right? And that's
Right.
Also mailing list as well. There are so many mailing lists available, so probably people stop checking their mailing list. So
Understood.
yeah, and also we try to do this on Twitter. So we tweet about new things, but not everyone is doing Twitter. I don't know. There are so many different channels, and we try our best to put this in different channels. But still, it means it's not always that we reach to the users. So I don't know if you know your channel and recommend it to go the channels out, how to reach.
Great.
You. Yeah, we can do something.
Yeah,
but it's
thank you.
important for us.
This is very, very helpful for people like me. It's really.
Thank you.
Are there other questions, folks, or comments? If not, I will thank Sergey for a very, very enlightening talk. And Daniela and Carlos, do you want to add anything?
Not really, but just say again, thank you to Sergey, and just to state my hope that we will really see this line list applied in models. We've seen already papers that use them in planetary atmospheres. I hope we see this in models that everyone can use also for cool stars very soon. I'll mention as well, and this is an initiative that we have discussed in the organizing committee of the commission before, that there is a plan for having in the website of the commission a list of useful resources like databases like this and news, right? So this would be the right place also for perhaps for these communications, or one more channel.
That I could only say thanks for that. If you've ever had to have a young student, I mean really young student, and you're trying to introduce to this kind of work, the amount of pointing to useful resources is almost overwhelming. And so having this library is excellent.
All right, so thanks everyone for coming and joining us. Thanks a lot, Sergey. See you next time.
Thank you very much for having me.
Thank you.